Welcome to the video on law of mass action, which basically is exactly the same thing, another way of saying the equilibrium expression. So the videos you've watched already, and the way I'm going to say in class, I call it the equilibrium expression when I talk about something like this. But on the AP test, it might call it the law of mass action, so I just want to make sure that you know what that means. It basically means that if you have reactants going to products where the little letters represent their coefficients, you can write the equilibrium expression by putting the products over the reactants, and each chemical is raised to its coefficient, whatever that happens to be. And like I said, this is called law of mass action. Now, 9 times out of 10 this unit, we're going to talk about Kc. Kc means the equilibrium expression of the concentrations, which is why these things are in brackets. You can also have Kp, which is for pressures, Ka, which is acids, we're going to do that next unit, unit 4, Kb, bases, also unit 4, and Ksp is the solubility product constant, and we'll be doing that when we hit reactions unit. All of these collectively are Keq, the equilibrium constant for any equation, any equilibrium. What does this depend on? The Keq will depend on temperature. You change your temperature, you're going to get a different Keq. It does not depend on concentration, because the concentration, as you saw in one of the videos, or you will see, I'm sorry, in one of the videos, as the concentration changes, the equilibrium will just shift back to be the same ratio, because this is all about the ratio of products to reactants, not actually what the products or reactants are. It does not matter about mechanism, it doesn't matter how you get there, this is just talking about what the ratio is once you get there. Non-reacting substances will just change your concentration. Since they have no bearing on the reaction itself, they're not going to have any bearing on the Kc, because this only has to do with products and reactants. And again, catalysts, that'll just get you there faster, which has to do with kinetics, but this doesn't matter on how you get there or how fast you get there. The equilibrium expression is only about what it looks like once it's at equilibrium. If you have a Kc that is greater than 1, that means that your numerator is bigger than your denominator, which means that you have more products than you have reactants. And so this one says products are favored. So basically, if we were to draw the equilibrium arrows the way it should be, in this case, you'd have a lot of the reaction proceeding forward and some of the reaction proceeding the reverse. Conversely, if your Kc is less than 1, then that means your denominator is bigger than your numerator, which means the reactants are favored. And if you were to draw this, you would have a equilibrium arrow that looks kind of like that, where your reaction is mostly proceeding in reverse. And then if your Kc is equal to 1, that means you have the same concentration of products and reactants, and then you have exactly the same arrows going forward in reverse. Again, the rate of these arrows is exactly the same, whether it's product favor, reactant favor, whatever. The rate at which products move to reactants and reactants move to products is the same. This just tells you how much of my products I'm going to have relative to how much of my reactants I'm going to have at equilibrium. And then lastly, let's talk about the forward rate versus the reverse rate. So if we had this reaction, so we had E going to G. If we wanted to write the equilibrium expression of the forward reaction, so K sub F, we would write G over E. This is the products over the reactants. If we wanted to write the equilibrium expression of the reverse reaction, it would be E over G, because in the reverse reaction, these are the products and those are the reactants. So the relationship between these two is that they're inverted, which means that if you have Kf, that is the inverse of Kr, which is a handy trick when you get to the test and you're trying to save some time. If they give you the forward reaction and they want to know what is the equilibrium expression of the reverse, you just take the inverse of it, and vice versa. It works just the same. Thank you.